Hello physics students. So as you know, this course is called Electricity and Magnetism. But maybe you're thinking, where's the magnetism? Up until this point, we've been only studying like electric fields, Gauss's law, all these techniques to find electric field, and then the last topic, electric current or electricity. Well, today, in this video, we move on to the second part, the magnetism part. We'll learn all about this thing called magnetic field, what it does, and how to calculate it. And then we're going to move on to a third part, electromagnetism. We're going to see that the two are actually linked. They're not two separate things. That's why this course links the two, and it's called electricity and magnetism. You cannot separate them out. That's what we'll learn in the final phase of the course. But today we begin magnetism. And before I begin with today's information, I want to give you an overview of magnetism. Remember when we were studying electric field and charge? We broke that up into three parts. The first part was more or less an algebra-based treatment, figuring out the forces, the electric fields, the voltages, and the electrical potential energy of just dots of charge. And then that was like typically what you would learn about electric field and whatnot for a non-calculus based course. Then we went on to a second part, distributed charge, where we spread charge along lines, along arcs, along circles, over a disk. And we calculated the electric field by direct integration, splitting up a line of charge, for example, into little dx's and therefore little dq's that acted like a proton or electron. So we could use kq over r squared and adding that up through integration to find the net electric field at a particular point. And that was pretty intense in terms of calculus. And then in the third phase, we moved into Gauss's law, a law that allowed us to use this idea of Q enclosed in a Gaussian surface to calculate the electric field technically without any serious integration. And so that was the three phases. The same thing will happen in magnetism. Today, we're going to begin what we'll spend about a week on, which is more or less just algebra-based magnetism. And so that's what typically is learned about magnetism in a physics course that's non-calculus based, phase one. And then in phase two, we're going to learn something called the Biot-Savart law, which is looking at the magnetic field caused by a little tiny bit of, we're going to find out, current, and then integrating to find the net magnetic field. That'll be the most difficult thing we'll do in this topic. And then in the third phase, we're going to move on to basically the equivalent of Gauss's law, but for magnetic field called Ampere's law. So three big phases. But today, as I said, phase one, the algebra-based treatment of the magnetic field. And in order to use that only algebra, we have to confine our studies to long straight wires. And remember what I'm talking about, long is like an infinite length, but infinity is always relative, just like with electric fields. We could be talking about a wire stretching from one side of the room. As long as you're not near the ends and you're not very far away, if you're close to this long wire and you look either way, it looks like pretty much it's infinite in length, and mathematically there's not much difference. So let's begin. So the first thing you need to realize and know is what creates magnetic field. And in the case of electric field, it was charge, protons and electrons. In the case of magnetic field, it's electric current, moving charge. So that's the first thing. And then the other thing, you need to know the direction and the magnitude. So let me first talk about the direction of magnetic field. When it came to the electric field, we had proton positive, electric field points away from it everywhere. An electron directly towards the electron. With magnetic field, more complicated. Let's suppose I have an infinite wire. Well, this is just a dowel, finite in length, but let's suppose it stretches very far in either direction. And let's see, I got to think about this for a second. So yeah, we're going to have current going this way in the wire. So it creates magnetic field all around this wire. But it doesn't point away or towards the wire, it points around the wire. And so I have a little diagram here to show you. So let's suppose now the wire's going like this, the current's coming straight at you. The magnetic field goes around like this. Maybe I'll get closer to the camera so you could see this easier. Okay, so there is the wire, and the magnetic field goes around like this. Now I say goes around, it doesn't really move. It stays there. These arrows are stationary. It's not like they're spinning around like this. So they're stationary, but you could see that the arrows do not point directly toward or away. And so I have here a red line indicating a radius vector going away from this wire, and you could see that the magnetic field is perpendicular to any particular radius vector coming straight from the wire. So that's the first thing. And if I flip the current around, then the magnetic field would go, all these arrows would flip the opposite way. So it goes clockwise or counterclockwise depending on the direction of the current. So that's the first point. And you need to be able to figure out the direction. So here we begin. Magnetic field around a long wire, quotes because that's relative. So now this becomes tricky to sketch. So as always, when we have vectors pointing out of the board, because now we're in 3 dimensions, we draw a dot with a circle around it representing like an arrow pointed straight at your eye, the shaft of the arrow and the point of the arrow. So you see these going around in a counterclockwise direction, whereas if the current's going into the board, again, this is like the feathers of an arrow receding, flying away from your eye in the shaft of the arrow. So the arrow's going, so the current's going in like this. I forgot to label it here. Then the magnetic field goes clockwise. So the way you remember this, one tool is what's called the right-hand rule. Okay, so here's how you use the right hand. And by the way, right-hand rule number 1. There's another right-hand rule we're going to learn in a couple days, a couple videos time. But right now, right-hand rule number 1, what you do is you put your right, and I underline that because you'd be surprised how many people call me over, hey, I don't know why, I'm getting a different magnetic field, and they're going like this with and I look and I say, you're using your left hand. Oh, man. And these are people getting A's in AP Physics right there. So sometimes it doesn't matter how smart you are, you lose your concentration, you start using your left hand. Make sure it's your right hand. You put your right thumb in the direction of the current. So see, I go like this. My thumb is coming out of the board, my right thumb, because that's the direction of the current. The 4 fingers naturally bend in the direction B rotates. Again, B rotates is in quotes because it doesn't really spin around. The arrows are stationary. So the other thing is, it's important to realize your fingers don't tell you the direction of the magnetic field. For example, if I said, what's the magnetic field down here at this point, and these arrows weren't here, a lot of people go like this, oh, it's to the left, right? Because they're seeing there, they put their thumb there, oh, it goes to the left. No, above the wire, it's to the left. But if you look below the wire, my 4 fingers come around and point to the right. So be careful. This one, if we do the right-hand rule, well, we put our thumb in the direction of the current, and my 4 fingers go this way, so I know the arrows are drawn that way. So that's the first thing, the direction. Go ahead and jot this down. I'll create a little pause. Okay, so the next thing, the magnitude, the size of the magnetic field. We also want to calculate it. So here's the formula for a long, this only works for a very long wire, B equals mu 0 I over 2 pi r. And this will give you, if you plug in the current in amps, and pi, of course, pi, but radius in meters, and mu 0, this constant, you get the magnetic field in the unit of it is Tesla. One of the units. This is another unit. We'll talk about that later. So Tesla. Let's take a look at an example. So first one, determine the current required to match the Earth's magnetic field of 50 microtesla, Earth's 50 microtesla field at 0.1 meters from a wire, 0.1 meters. So I mentioned one of the things you know from science class that the Earth has a magnetic field. That's why we could use it for navigation. Well, in New York State, it's approximately 50 microteslas. In other words, 50 times 10 to the minus 6 teslas. So we want to know, all right, that's the Earth making the magnetic field. If I wanted to make my own with a wire, how much current would I need? So here is my magnetic field expression, and I'm solving for I. I move the 2 pi r to the other side, and the mu 0 I divide, and that leaves me I all by itself. So let me create a pause slide. You copy this down. And moving on, plugging in my data, 50 times 10 minus 6 teslas, and then the 0.1 meters, mu 0, and I punch that on the calculator. I get 25 amps of current to produce a magnetic field about that far from a wire that matches the Earth's magnetic field. All right, let's take a look at another example. This is obviously a real simple one. The AP is going to go in deeper in more difficult, more challenging problems. So let's take a look at something else that you might find in an AP test. So determine the location where the net magnetic field is 0. What I have is 2 wires oriented on an x-axis. Of course, the wires are coming in and out of this board, so they're going like this. This wire has 3I coming right at your eye. This wire has just I going away from your eye. X equals 0, X equals D. And notice I drew this bigger because there's more current, so kind of give me a visual. So I want to find out where, over here, over here, over here. First thing I have to do before I begin calculating is to figure out the region. Which of these 3 regions is it possible for the magnetic field of these 2 wires to cancel and get net magnetic field 0? So if I look at this wire, the magnetic field, I use my right-hand rule. Above the wire, it goes to the left, but over in this region, it goes down. And then, well, I can't bend my wrist like that, but you'd see that if I could, in this region, it would come up. So down over here, up over here. So what I'm going to do is I'm going to draw an arrow down like this. Oops, I meant to call that B3. You could see it from the colors, but if you don't have colors in your notes, you could just label that B3. That's the magnetic field from wire 3. And over here, B3 goes up like this. And in this region, we have B3. Well, that's still going up this way, right? Current up this way, magnetic field up that way. But further from the wire, shorter magnetic field. So I'll do this like B3. So those are the magnetic fields caused by this wire over here. How about this wire? Right-hand rule again. So I put my thumb not out of the board because the current's coming out here, but into the board. And I see my 4 fingers of my right hand go like this. So above the wire, the magnetic field points to the right. Over here, it points down. And anything in this region, it's going to point up. So let me sketch those magnetic fields. So I've got B1 like this. B1 like this, and B1 over here, even shorter, but if I draw it short proportional, you won't even see it. The magnetic field could never be 0 here. The magnetic fields both add, they're in the same direction. It could also never be 0 here, because yes, these arrows are in opposite directions, but we have a smaller radius for the bigger current. So smaller and bigger means this arrow here is always going to be bigger than that one, no matter where I move over here. The only place where they might be able to cancel is over here. If I move to the right place, then this larger current is a larger radius away, and that balances out to and makes an overall same magnetic field possibly as that one. So now what I'm going to do is calculate 2 magnetic fields, set them equal to each other. But I have the currents, I need the radii also. So let's begin by, if this is x equals 0, then the distance all the way to this point is going to be x along the x-axis. That turns out to be the radius for the 3I current. The radius for this is how far, for the I current is right here, how far away we are from this wire. So it's essentially from here to here. And if you look at what we have on the x-axis, this whole distance is x, and this distance is d, right? You see, so that's d. Maybe I'll do it down here. This is d. So this is obviously x minus d. And that turns out to be the radius for the other wire. Okay, so we have the currents, we have the radii. We can proceed to our calculations, but first I'm going to make a little room. Okay, so I'm going to set B3 equal to B1. So that's the idea of how I know the net magnetic field be zero, because they're equal in opposite directions. Now let's plug in the data. We've got on this side mu 0, 3I over 2 pi, and that radius is x. And on this side, we've got mu 0, just I, over 2 pi. As we can see, the radius over here, x minus d. And now all that's left is a little algebra to solve for d. What you could see is the mu zeros cancel. The 2 pi's cancel. And so does the variable I. And what's left is 3 over x and 1 over x minus d. So I could cross multiply. I get x times 1. And on this side, 3x minus 3d. Right? That's what happens when I distribute the 3 into x minus d. And on this side, just 1 times x. I subtract 1 from both. I subtract 1x from both sides. This side has 2x on it. And I add the 3d to the other side. And I get x equals 3/2 d. There is the location of where the net magnetic field is zero. Everywhere else on this line, it's not zero. Unless maybe I go to an infinite distance, right? Then the magnetic field's zero because of this formula. Both of them are zero. All right, so let's move on. I'm going to do one more example. Okay. All right, if you need a moment to copy this down, to catch up, I'll create a pause. All right, let's take a look at our final example, example 3. Oops. Nice. So here is a particular set of wires. One has, of course, the wires going in and out of the board like this, and this wire is going in and out of the board, but here the current's coming out, and this here it's going in, as you could see how I've drawn it. So I want to find the net magnetic field right here at at x equals a. This is the origin where x and y are 0. So what I'm going to have to do is find both magnetic fields caused by both wires and then add them together. But magnetic field, like all fields, is a vector, which means it has a direction, which means we may not just be able to add, we may have to use some kind of components or Pythagorean theorem to add these two magnetic fields. So let's see what happens. First, we have to find out what the individual magnetic fields are, direction and magnitude. So I use my right-hand rule, put my thumb like this in the direction of the current, and I see my fingers point so that the magnetic field caused by this wire goes around like this. So if I sketch in a radius vector, then I know that the magnetic field comes around and goes perpendicular to this line. And so it will point like this. I'm going to do, well, you know, if you want, you could get a piece of paper like this and, you know, get it nice and accurate for a 90-degree angle. And I'll draw it nice and long. So this is B for, let's say, positive coming out of the board. I don't know. You could use B1, B2 if you want. So that's one of the magnetic field arrows. Again, this has to be perpendicular to the radius. So here's another radius for this wire, okay? And so that would create a magnetic field that would be, oh, right-hand rule first. Thumb into the board, and then I see my fingers go like this, so the magnetic field goes around like this. So right here it goes like that. So what I'll do is I'll use the paper to help guide me, draw a 90-degree angle. And it will be something like this. Now, so what you could see is I can't just add these like, you know, like numbers. I have to do a vector sum. And the easiest way to do this is to realize that these two have vertical components that cancel. Whatever Teslas we have this way, you've got that way. So what we're going to do is take these two horizontal components, Bx and a Bx over here, and add them. But we could see these are the same magnitude lengths. So the first thing we could say is that B net is equal to 2Bx component, which is then going to be, if you just use trig, it'll be the hypotenuse. And if I put a theta here, I'll multiply by cos theta. So that's how I find the net magnetic field. I'm going to find the length over here, and then multiply by cos theta, multiply by 2. Let's fill in the pieces. So the formula for B, well, I erased it, but remember it's mu 0 I over 2 pi r. But r is right here, which I'm going to have to plug in from the Pythagorean theorem from the data given, is this squared plus this squared square root. So messy. There. There's the magnetic field caused by or just the length of one of those arrows. Now the cosine theta, this came up in an electric field. You could actually eliminate that cos theta by realizing that this theta here is the same as this theta up here. And so now we can find cos theta in terms of the original variables given, because cos theta is the adjacent side over the hypotenuse. And the adjacent side is 2a. So I'll put that right here. And the hypotenuse is that square root of a squared, oops. Okay. This is the cosine theta. Okay. And now all we have to do is just sort of touch this up a little bit. So 2 and 2 cancel, but we still have a 2 on the top over here. So we could say B net is equal to 2 and then the pi survived, right? So we'll leave that there. And then what we have under the radical is 4a squared plus a squared, which is 5a squared, square root. But what we have is square root of 5a squared times square root of 5a squared, which just gets rid of the square root. So we have 5a squared like that. One of the a's cancels. Oops. Got the 2. Okay. Now, one thing I want to mention, I'm going to do this a lot of times, just like with Gauss, electric field, Gauss's law, distributed charge, unit check. You should always compare to our original formula, mu 0 I over 2 pi r. In other words, we should have the units of mu 0 amps over meters for magnetic field. And we do have a mu 0 in the top, we've got an amps in the top, and we've got a meters in the bottom. So the units check out. Trivial in this case, but later it's going to be a lot more complicated. All right, so let me create a pause to allow you to copy this down. All right, so that's it for today for this video. We have begun with calculating the magnetic field for an infinite wire, the algebra-based portion of magnetism. Remember, so we're going to do magnetism 1, all algebra-based stuff, and then magnetism 2, Biot-Savart law, and magnetism 3, which is Ampere's law. One thing I want to mention before I go is that I didn't tell you yet what the magnetic field does. Well, like the electric field, it creates force. Electric field made electrostatic force. Magnetic field creates magnetic force. But it's more complicated than the electric field, where we had an electric field, proton just had a force going with the electric field, electron opposite the electric field. It's going to be more complicated, but that's the subject of another video. All right, so I hope you enjoyed the physics video, learning about magnetic field. I'll see you in the next physics video.